Okay, so moving to the last phase of the course on reinforcement learning and approximate dynamic programming, and that, I guess that's sort of converged to standard language now, where reinforcement learning means model-free in quotes. So, what do I mean by this? In both cases, there's a model. It's absurd to think you don't have a model. In reinforcement learning, you can look at the input-output data and learn what you want to learn. What do you want to learn in optimal policy, for example, or some other parts of the model? The approximate dynamic programming, you use a model, and you have to, the whole algorithms are based on knowledge of the model. And so they're often more appropriate for simulation. So instead of looking at the input-output data you get from Wall Street, you have a simulator of Wall Street, and you use that to tune parameters in the model. And so it'll be clear as we go along as well. And so the guys at MIT tried to coin neurodynamic programming. Which I think is sort of fun. I think it's too bad it hasn't really caught on in a way. But it's a good book. So this is by Betsikas and Tsitsiklis. He's done in 96. The field didn't exist until recently. But so this guy's the hero, John Tsitsiklis. So this field, the thing is that some really beautiful algorithms came out of the CS community, and I can say without any arrogance that they were very creative, but they had no background in doing the analysis. So when the guys who invented TD learning came along, there was no foundation to analyze it. It just looked like it came out of nowhere. And it was actually a thesis, John Tsitsiklis advised a thesis that just blew it open. I mean, very, very transparent what was going on. And I'll clarify that. Same with Q-learning. I mean, Watkins came up with this algorithm called Q-learning, and his Q function is the Hamiltonian of optimal control. It's just right out. Anyone who's had a background in control would see that right away. But he wasn't from that background, and there was no background. There's no foundation at all. So the CS community really did some beautiful work and come with algorithms, but it was the EC community and mainly John Tsitsiklis and his students who have just came up with a beautiful scientific foundation for the whole subject. So I really warn against picking up some of these books. Like, I don't recommend Powell. What's it called again? It's just called Approximate DB. I mean, I recommend it. It's good for applications and all. You can see some examples, but it doesn't. I mean, he's not a CS background, but he's from a similar. He's a great guy, but there's very little foundation to explain why you would do this and what the alternatives are. Why is the variance suddenly huge when I try it out in this experiment, and the variance is low in another? I mean, you want to understand why it doesn't work. Most of the time, these algorithms don't work, and I want to explain to you why. So this is one book that definitely I recommend. There's another book, there's Borkar's book on stochastic approximation. By Borkar, and it's really technical, but it's the best book out there in terms of the foundations. Unfortunately, Borkar's not the best writer. He's a wonderful scientist, but he's pretty technical. I think his paper with me might be better. So we wrote this together during my first sabbatical when I was in India. And this is actually the foundation for his book. And we weren't as ambitious, and we weren't trying to do as much. This book tries to do a lot, and it's a very small book, so that's why it's very dense. So this is a more leisurely treatment of the same topic. And then there's this book chapter that I distributed at the beginning of the course. If you look at the resources box, you'll see that reference. Okay, so what do we do with this? What's the goal? So I mean, I've gone through and I've said all this. What are we trying to do? Trying to work with 10. So let's stick to the discounted case. I know I haven't really treated that in class, but you touched on it in the homework. So I sort of avoided this just because I wanted just one optimization criterion. But a lot of this work has been done in the discounted case, and a lot of the description of algorithms is easier in the discounted case. So I'm going to jump to that. So in that case, for a given policy, you would have a value function that looks like this. H star is the minimum of all inputs of this, and it solves the DP equation just like we've seen before. And it's and so there it is. So it turns out that the DP equation for total cost that I wrote down is exactly this. This is the discount. We derive a discount, the dynamic program equation for the total cost, and I told you how you could take discounted cost and map it to total cost and input. So, what are the things we'd like to do? Well, most problems we come up with are in a general state space. I know dollars are integers, but if you have a lot of dollars, you might as well round them off to continuous numbers. Anything in physics, anything you look at, you have real numbers. And you try to solve this equation for every x. It's real, you're dead. If you try to use binning, those of you who've done the homework, you see immediately you get this curse of dimensionality. So I say binning, I mean replace, say, the real line by a bunch of lattice points or something like that. Well, if you're going to do that and you want an accurate fit, then D is going to be too big to think about. That's absurd. So D is 10 to the 10th. So the point is that that's what people typically frequently just do. They go and they bin the state space and they go on with it. It's a crazy thing to do. It's much more reasonable to bin, in some sense, or have it parameterize the function you're trying to solve. So in TD learning, you have a basis. So somehow you get some intuition. Somehow, just by magic, you get a bunch of functions psi I which form a basis. Maybe they're Fourier bases. You know, maybe it's 1 cosine x, sine x, cosine 2x, sine 2x, and so forth. And but truncated up to d, and then you have some coefficients. And I'd like to minimize over theta the norm between h and h theta. You know? Which might look a little odd. You know, what's the norm of a function? Well, I've been saying all along that I'm considering functions as column vectors, so there should be a norm. And what you mean by a norm in TV learning in TV learning, you take a particular norm, and that's the only way you get an algorithm that works. There's one norm that gives rise to a good algorithm, or maybe, I mean, little perturbations of this, but it's an ergodic norm. So that x is capital X, and it's the state in steady state. And so this is for this problem here. So you apply a particular policy. So basically, in TV learning, you're trying to approximate this function for a fixed policy. And that's it. And the way to do it is you assume that there's an ergodic steady state, so it's a stabilizing policy. I mean, the whole theory was developed for finite state spaces, so it wasn't really an issue. But anyway, you assume that there's a steady state distribution. You take this particular norm, and you get a beautiful algorithm. You know, there are some perturbations of this you could take, but you take an arbitrary norm, there's no theory. There's no algorithm, there's no theory you're going. So it's a really clever choice of norm makes this tractable. Right? So that's one example. And you can say it'd be hard. I mean, if I go through and I don't know, if you want to minimize this, you've got to take the gradient and set equal to 0. You can imagine how tricky that is. I mean, for one thing, the gradient is going to depend on h, which is the thing you want to solve. So it looks intractable, but it's not. It's a beautiful algorithm to solve this.
Is our goal still to find a u, like it was in the past? Are we still trying to find this?
Well, I'll put it back to you. So why would I want to compute h for a given policy? That's a good question. I want you to answer. I know in about 60 seconds you will. I'll just wait. I mean, somebody gave me this function. What might I do with it if I was interested in control? We didn't talk about this in the discount case. We did in the average cost case. If we had a value function, what we do with it?
Find the approximating the optimal policy.
Well, and how would you do that? Yes, you'd like to find the approximately optimal policy.
Yeah.
And how would you do that given just one h? How would you, given that policy phi, how might you improve it as a hint?
I mean, we can take it as the input to a value iteration, but then we
but not value iteration. You know, so policy iteration is where you're given a value function and you use that to define a new policy. So one application is. So to approximate policy iteration. And so what you get is a new policy. So given your best approximation over here, so once you solve this problem, you get the best fit you can. You solve this argmin to get a new policy, and you win again. And I don't want to jump ahead of myself too much, but there's some issues with this. It's not. What are the issues? I mean, there's some issues. You're stuck with this damn norm is one of the issues. If pi is concentrated in a single point, then this norm is not very informative. So there are issues. And that's this exploration versus exploitation. So the fact that you're stuck with one norm is an issue. That's a problem.
Pi is a function of your policy too, right?
Yeah, that's right. Yeah. And you don't know where you want to explore yet. So it is an issue there. Thank you. That was good. Any other questions? So that's one application. You can go through this. This has a solution. The most beautiful, elegant solution you can do. But again, there is this issue of the fact that I do have to keep doing this over and over again for approximate policy iteration, and there's an issue of exploration. It's how do I explore? So what Watkins did, and I wish someday will tell me why it's called Q. He called this the Q function, and he said, let's learn that. So
doesn't it stand for quality, like these things value?
what's that? Tell me what?
I think it stands for quality.
Really?
It was value function, so it was just like, all right, the Q, this is the value of the quality function.
Quality function.
I think so, don't
All right. I thought it was the name of his girlfriend or something. Quality. Okay, quality. All right. So the quality function. And by the way, this is, if you go back, it's if you replace PU by the generator flew around, it's cost plus generator times H. It's the Hamiltonian basically. But if I denote, it's a new notation. Now, it looks like I'm just playing with ink, but suppose I define, when I put a lower bar, I take the minimum of U, of Q of XU. That's a notation. Well, what is that? It's a min, and that's Q, that's 8 star. Okay? So I'll put it in parentheses. Let's see. What I can do is I can say, this is Q of XU. So this is Q of XU. It's C of XU plus beta PU. And you think I'm going to write 8 star? I'm not. I'm going to write Q lower bar. They're the same thing, right? Okay, so what the point is, you can take a fixed point equation in 8 star, the original thing, and you can replace it by a fixed point equation in the quality function, or Watkins. 1989, is it? That's right. In his PhD thesis. And why would you do that? Well, I'll explain by the end of the lecture. And so now you can say, well, let's try to do the same thing. let's try to approximate this. So let's say that we have q theta of xu is equal to, what would it be? Well, this is q. I know the cost function, so I would probably take it c plus some basis. So now I've got a basis as a function of x and u. So this is stuff I don't know. I don't know H star. I don't know PU maybe. You know? I don't even know the system. I don't know anything. And I just call this some function of x and u I'd like to solve, and I construct a basis for that instead. And my goal then is to approximate this equation. And so if you'd like, you could take the difference and take the norm squared like I did before, something like that. All right? And how would we do that? So that's what the Q-learning algorithm should be. It isn't yet. Okay? So if you look up Q-learning in a book, you'll get an equality there. So Watkins in his thesis found a simulation-based algorithm to solve this exactly. You know? And that he did that by parameterizing everything. Okay, so Watkins wanted equality. So I'm actually lying a little bit. So you know, this is the goal. I'd love to come up with an elegant theory for approximation of the Q function. There's some ad hoc things you can do, but there's some technicalities that make it hard. You know? So I mean, I have one paper, the deterministic setting, that works, where you can do this, where you can look at, you know, which is something that hopefully we'll finish up this year. But largely this is still an open problem, is how to get good algorithms to approximate this given a basis. But what's beautiful about this, though, is that now, like in Watkins' algorithm, you don't know anything at all. I don't know P, it turns out. I don't know H star. I don't know anything. I just plug in some crazy randomized policy and watch. Randomized policy, that's crucial, otherwise it doesn't work. You know, so some function of state and noise. You know, and you can learn the optimal theta that gives you equality. So that's it. So these are what we want to do over the next remaining 4 lectures. I mean, there aren't that many lectures left, over the next half dozen lectures. And the algorithms are pretty simple once you understand a little bit about something else. So stochastic approximation. So these problems, TD learning, Q learning, actor critic, all these algorithms are just one, you know, step away from what's called stochastic approximation. And so that's what we need to do. So you need to learn what that is. Stochastic approximation is just as I mentioned last lecture, it's just a generalization of simulation, of Monte Carlo. And once you understand that, these just pop right up. And not only that, once you understand stochastic approximation, you understand why things go wrong, why variance might be so large, because you have ways of understanding the variance, you know, approximating. And this, yeah, I mean, and you saw that the first homework problem was given to you intentionally to show you how awful things can be. So hopefully we'll come back to this, and I'll explain to you why it didn't work, and why you can make it work. Okay? Not today. But, you know, before the course is over, you better see why this didn't work. And so some theory here will help you see that. All right, so what do we have here? We have these sort of fixed point equations we'd like to solve. And we need a general foundation for addressing these problems. Here's the general setup. So I've got I'm going to write down a general problem, and I'll explain why this is exactly an instance of that general problem. I've got theta is some parameter in RD, and I've got a function. Parameter, a function, n, and I want to solve this equation. Now, what does this have to do with that? Let's do that first. So I claim, if I understand this problem, how to solve problems of this form, by all the other problems. So how on earth does this have anything to do with this? It takes some work. Okay, so for Q learning, so what happens there? Well, the way Watkins thought of this is his size were everything. He actually considered QXU that big matrix. He just wanted to learn all those entries. So Q is a matrix, and just vectorize into a big vector. So Q is theta. I'm not theta. Q is, sorry, how do I get this in here? With the correspondence there, I can't say it. Q is theta in this correspondence. That's the first thing we didn't recognize. Think of Q as a big vector. Q of X2 is a bunch of numbers stacked up together. He looked at finite state space, finite action space. You have a whole bunch of numbers you can stack that to form a vector. Call that theta star. That's what you want to learn. All right. So he did not look at this particular parameterization because he wasn't thinking about approximation. He was thinking about exact computation. So I've told you what theta is. I've got to have what n is. Let's go back to Watkins' algorithm. Now, I want to learn Q of XU for each X and U. What am I going to do? Well, and I want to have, say, expectation of theta n equals 0, I've got to define f and I've got to define n. Well, it's right there. That's an expectation. So I'll do is I'll put the minus q on the other side. Is that the direction that I'm going to turn the end? Yeah, of course it is. So f is just going to be this minus this. And the randomness comes in here. That's a conditional expectation. So n is what? What's its distribution? So this noise here depends on the parameters, the coefficients x and y. There you have it. So computing q is within this sort of equation. Computed exactly. You just have to. It's just a little bit weird because of the notation again. I'm thinking of this quality function, the q function, as a parameter. It's a bunch of numbers I'm trying to learn. Okay. Remember, that's what this means. This is an expectation. The expectation of that is that. Because PU is defined to be the expectation of at time t plus 1 given your previous state or your previous action. All right. Enough of you are nodding, then I'll move on. Okay, so in 2D learning, it's even easier. I mean, it's just immediate. If I wanted to try to minimize that expectation, I take gradients, I'll get that. It's a condition for optimality. You sighed too late. All right. All right. So there's an ODE. Well, first of all, I'm going to give this a name. Let's just call f bar, that expectation. The ODE is d dt theta of t equals f bar of theta of t. And what we're going to do is we're going to set this problem up to assume that this is a well-behaved ODE. And what we want is this ODE to converge to the solution to that equation. So this would be a stationary point of this ODE. But you need more than that. We're going to have some assumption for that stationary point theta star is actually attracting. We want theta of t to converge to theta star for each t. This is going to be some way of how we set up. There's a problem of how we develop algorithms. We're going to design the algorithm because I can always multiply this by -1. Or if f's a vector, I can multiply by some matrix. I can multiply by inside. I can maybe multiply it by a matrix that depends on theta. There's all sorts of ways of manipulating this equation to get equivalent equations. So I'm going to manipulate this equation so that that it's not, well, obviously it's a stationary point, but also stable. All right. Now that's it, we're done, right? Because I just go and run this ODE and I've converged. But, of course, n has a complicated distribution. I don't want to have to perform this integration at every step. So what do you instead? Well, what Robinson and Monroe suggested in 1951 is to replace the differential equation by a difference equation. And do I have AT as mine? And if I had some small step size theta t, I could plug in this expectation of value theta t, but let's not. And I tried to go from subscripts to superscripts. I should be consistent with it. So that's stochastic approximation. Is to take this Fourier differential equation, which is incredibly complex, and replace it by a sequence of steps like this, where n of t has distribution n for each time. Now, if you pick up a book on stochastic approximation and look at the papers, they'll immediately say where n is IID with distribution n. And it just completely forces everybody into a mind trap if that's how you have to do it. And there's no reason at all it has to be IID. It might be much better to not make it IID, to make it Markovian or something like that. And applications, often it can't be IID. So you've got to be careful of that. So the only thing I'll assume so far, I'm not going to give any complete proofs, but when I go through the proof, the sketch of the proofs, I will assume an IID. So it simplifies analysis, but it's not necessarily a good thing to assume. It's not necessarily possible in applications. Again, especially in applications to reinforcement learning, where the noisiness is coming from the real world, and there might be a lot of dependence. It might be far from ID. And moreover, if we have the freedom to put in exploration, we might add a lot of variance to the algorithm if we put in IID exploration. It might be much better to put in something deterministic. So it's a big question. So just be careful with that. So there it is. So under very, very general conditions, the limit points of this will be the same as the limit points of this. They're the same limits.
Should that be the expectation of f?
Thank you. So again, it looks like I'm testing you again, but I dropped the expectation. Now, that's the beauty. See, I said that to run this ODE would be incredibly complex, because at each time instance, you'd have to compute this expectation, which might be an integral over some m-dimensional space. So what you do is you just drop the expectation and cross your fingers. But Robinson and Monroe were not computer scientists; they were statisticians. People in EC do it too. Come with algorithms without any justification. But they knew what they were doing, and they developed some very nice tools for analysis. So again, the program is, I have my fixed point equation I want to solve. I set it up so that the ODE is nice, and the program. speaking as engineers, the programmers, we want to design this function f so that we get these two properties solved. So like for Q learning, do you remember I was really concerned about where the minus sign was? I wrote minus Q plus C plus beta. I was saying, I better do this right. I better have my f defined correctly so my ODE will be stable. And that's the normalization I would need. I don't want, if it's stable with f, it's not going to be stable with minus f. And then secondly, run this. We need some conditions.
Yeah, can we clarify that a little bit more?
Yeah, sure.
Is theta t a random variable, or is n of t plus 1 supposed to be a realization of the noise?
Yeah, so let's see. So we have this ODE, which is impossible. So I just dumped an algorithm on your head, and I said, instead of an ODE, let's look at a difference equation. And then it looked like I forgot the expectation, but I didn't.
But I'm just trying to figure out whether we're dealing with a random variable or not.
Well,
you just dropped
n is random.
So that means f of the n is random.
So f, yeah. And so this is random, so theta is random. And so actually this converges with probability 1.
Ah.
And under conditions, which I'd like to explain to you, obviously not today, but between today and tomorrow and maybe. And it's really, well, I've got 10 minutes, don't I? So an example might clarify things. So suppose I wanted to minimize overall theta, the expectation of theta minus g of n squared, g is some function. Now we can solve this, but let's pretend we can. Okay? So we know then that we would take the derivative. And it's actually quadratic. And for simplicity, let's take it scalar. I just don't want to have to deal with you can expand this out as theta squared and the cross terms and all that. But I can also justify taking the derivative inside. And the derivative quadratic is just 2 theta blah blah blah, and then divided by 2. So the gradient of this, the gradient of the square is just the difference. And so obviously theta star is the mean. Okay, so that's something you learn in probability, that one justification for the mean is it minimizes this L2 norm between g of n and theta. Okay, but forget you know that. Okay, I mean, if you wanted to compute a mean, what would you do? You'd take averages. You would do this, right? You would do something like this. You would take averages. But let's just apply this out. Well, actually, I should be careful. Forgetting my program. I've found an f such that f of bar of theta star is 0. The f looks like it's sitting in our faces. But I'm not going to get this convergence. you'll see I need to write g of n minus theta, not theta minus g of n, to get stability, as we shall see. Okay. And then I'm going to, and then f bar of theta is equal to well, theta star minus theta. If f bar was defined to be the mean of this, you know, and so let's see if I've got step one right. So f bar of theta star is 0. Looks pretty easy. Plug in theta star, nailed it. And what about the ODE? The second part of step one of the program is to look at this ODE and see if it's stable or not. But you can see now why I was very careful with the minus on there. When you get that, you see that this is a linear system driven by a constant disturbance in the life. And so theta of t, shall I just sort of guess? I think that's right. If you solve this linear equation, you get the initial condition response, right? And then you get the particular the response to the inputs. And so that thing as t goes to infinity goes to 1 exponentially fast. So that goes to 1, that goes to 0. So theta of t does go to theta star. Right? So that's the first thing you've got to check. Make sure that you define things right so it's a stable differential equation. Now run stochastic approximation. So got my f there, f, g of n minus theta. And this will work under general conditions. So as an example, suppose I take a particular case. Suppose I take AT to be 1 over t plus 1. Try that out. Well, I can unravel these equations. Shall I do it? I got time. Let's unravel these equations. That looks appealing, doesn't it? So what I did is I took a of t equals 1 over t plus 1, and I just multiplied everything through by t plus 1 to get rid of the a of t, a sub t. Okay. But you see what happens is I get the minus theta of t and the 1 there, they cancel out. And so I get a recursive equation. Just get your purple pen. And knock those out. And so you get, that's weird. The initial condition shouldn't disappear. Hold on. Nothing wrong here, right? So when I said t equal to 0, I don't want to kill theta of 0. I know it does matter. That's correct. When t equals 0. Oh, yeah. It gets annihilated in the first guess. So when t equals 0, I have theta t, and minus theta t gets killed off. So it is true. So you can all second iterate this equation, right? T plus 1, theta of t plus 1 is t times theta of t. And I substitute in, I'll do it once. Just to make sure you know, I can, if this is equal to this, well, I can say, well, theta of t, t times theta of t is t minus 1, theta of t minus 1, plus g of n of t. It's just an analogous equation. I'll replace t by t minus 1. Okay, so just, so what you get is that this is equal to the sum I equals, I guess, it's 1 to t plus 1. So guess what? I told you that we know how to solve this problem. Computing the mean of a random variable, you're going to get a bunch of realizations of the random variable, an average, and it's going to converge under general conditions. In particular, if n is ID, the law of large numbers holds. If n is Markov under the conditions we talked about, convergence holds. It's just this is a general approach that holds for any kind of problem, not just for this particular least squares problem. And so, in fact, all I need, this is when at is equal to 1 over t plus 1.
Everybody.
What I need actually,
But the professors. No, that's what we're supposed to have, but it's like a grad student.
No, I just done it.
I need the summation of a of t from 1 to infinity to infinity. That's exploration. It means I can travel a long distance if I need to. That's the motivation. So 1 over t plus 1 satisfies that condition because the partial sum is like log of t, and so it goes on. But secondly, I don't want too much exploration. If you look at the sum squared, that's finite. Well, if you square this, 1 over t squared is sum of it. So that's true. So this is but those two properties are all you need. So under those two properties, you can run this algorithm and it will converge to a mean, no matter what you do. The only thing special about this is it has minimal variance. So any gain satisfying these conditions, this will work. But this one will give you the smallest variance of all possible. So those are the things I want to explain over the next, day or so. And then the algorithms are trivial. So I want you to understand where these algorithms come from. Going through TD learning, Q learning, it's nothing. And so I'm really having to struggle with this. In a way, I feel like we're going to have to bounce back and forth. Because I know you guys are all eager to see these algorithms. And I'm eager for you to see the foundations. So we'll bounce around back and forth between theory and algorithms. Okay, it's going to feel a little bit crazy, but these are the things. I want you to see that this is all you need in general. The stability of these conditions.